Okay, this is a lot longer lesson than I intended it for to be, but that's okay. So I wanted you to watch that Veritasium. Veritas is Latin for a truth, and uh, Sium, the Sium part is an element. So this is an element of truth, is what this Dr. Derek Mueller, is trying to teach. And I saw him at an American Association of Physics Teachers conference just a few months ago, back in January in New Orleans, and he was fantastic. He his big belief is that people have such a misunderstanding of science; they're afraid of it and they don't understand it. And his goal is to make it so that people get it and that it's not so bad. But anyway, so you saw the video on the falling object. So let's go ahead and with free fall, all we're talking about is the only acceleration that exists is that due to gravity, to the gravitational field. Okay, so A is equal to negative 9.8 meters per second squared when we're dealing with these problems. And then all your other equations come into play. I mean, it's here it is in a nutshell. So all your other equations, remember you had, we did x is equal to the average velocity times time, and we found that the average velocity is v final plus v initial. I haven't used that one too much yet, and that v final, of course, is equal to v naught plus at, and then v final squared is equal to v naught squared plus 2a times x final minus x initial. And then we have the big bear, x final is equal to x naught plus v naught t minus or plus 1/2 at squared. So all those, we're doing the same darned equations, except that a now is equal to negative 9.8 meters per second squared. That's the only difference when we're talking about free fall, except in the first problem I'm going to show you, because we're on a different planet. And so the astronaut wanted to figure out what the gravitational pull was. All right, now the first misconception that students have is when you launch something in the air, when something is initially launched, the v naught is equal to something. Let's say 10 meters per second. The v naught is equal to something. Instantly, when it leaves your hand, instantly, whom, the acceleration, negative 9.8 meters per second. That happens instantly. All right, as soon as it leaves your hand. There is no, if your hand's still touching and push, of course you're pushing it up. Okay, of course you're pushing it up, but you throw it up, and once it leaves your hands, instantly the acceleration takes over. Then the rest, we just use these equations, except we have a minus 9.8. We have a minus 2 times 9.8. We have a minus 9.8 here. That's it. Not that hard. Okay? So let's take a look at what the problems look like. First problem. An astronaut on a distant planet wants to determine its acceleration due to gravity. The astronaut throws a rock straight up with a velocity of 15 meters per second. So that, talk to me. Initial velocity? I think so. And measures a time of 20 seconds before the rock returns to his hand. What is the acceleration and magnitude and direction due to the gravity of this planet? Okay, there's a lot of implied stuff here. One of the other things, here's what gravity does, and I consider it the big gravity monster. All right, so I'm going to draw you the big gravity monster here real quick. Here's the gravity monster. It likes to, and what it does is it eats velocity vectors. All right, so we got a huge velocity vector at the start, and then as the thing gets up into here, then the velocity is equal to 0. So you have no, because he's just chomping that he's slowing it down. All right, he's eating that thing. Then our gravity monster gets sick, okay, because he ate too much velocity. So he's all sick. He doesn't feel good. Ugh, so he pukes it back up. And the initial velocity when it's coming back down is equal to 0. The initial velocity here, for what I was saying, was 10 meters per second. Now the final velocity down here is going to be negative 10 meters per second. equals the final velocity when it's coming back down. Mother Nature loves symmetry. Okay, so let's do this problem really fast and then I'll go on to the last problem. An astronaut on a distant planet. Okay, so I've got an initial velocity here of 15 meters per second. I have a final velocity. What's my final velocity? You got it. Negative 15 meters per second. What's the time? 20 seconds. Well, we know what the acceleration is. We'll go minus 15, negative 15, minus 15 over 20. And I get negative 30 over 20, which is equal to negative 1.5 meters per second squared. That's not very big. The moon is about 1.6, is about 1/6 of 9.8. So things, that's not very strong. All right, out here, that was the initial, and then we'll look at this problem here.